So quadrilaterals are just figures that have four sides. Here we have four examples of quadrilaterals, including the square, the rectangle, parallelogram, and trapezoid. These are the ones we'll look at, and these are the ones where you'll find exactly these formulas on the Pearson formula sheet. It's not the only way to express these formulas, it just happens to be the way they're given here. I do want to take a quick look at them. So for a square, here the sides happen to be labeled as S. Because we know it's a square, we know that all four sides have the same length. And since area is just length times width, or height times base, or side times side, area here is S squared. A rectangle is just a square where the two sides don't have the same length. In other words, a square is a special instance of a rectangle. The area of a rectangle is often expressed as length times width, and that's what it is here because the sides are labeled as such. If you want to think of this as height times width or height times length, that works as well. Label them however you choose. For a parallelogram, we've now got base times height. Essentially, a parallelogram is a rectangle that someone sat on and it's tilted it slightly to one side. The reason here that base times height works is, in fact, the way the height is given here makes us think that we can pick up this that triangle, and drop it right there. So if we remove this triangle from the left-hand side and add it to the right, suddenly what's labeled here as base and what's labeled as height are the length and the width of a rectangle. And finally, the trapezoid now has only two parallel sides, where the rectangle, the square, the parallelogram, they all had opposite sides that were parallel. Here now we just have the top and the bottom that are parallel, and the other two sides can be any angle at all. In this case, because our bases have different lengths, we first have to take the average length of the two bases. So to get the average, we'll add them together, b1 plus b2, and we'll divide that by 2. So that's exactly what's going on here. Essentially, we just have b1 plus b2 divided by 2, and we've multiplied that by the height. Reorganizing this equation brings us to this one. You'll often see this equation as well as h over 2, or 1/2 h b1 plus b2. All you have to be careful of here is that b1 and b2 are the two sides that are parallel to each other. Using these formulas individually isn't what's tricky. What can be tricky is knowing which ones to use when we have compound shapes. So here we're asked for the perimeter and the area, just of this front shaded area. For these questions, we do have to assume symmetry. For this type of problem, we do have to assume symmetry where needed. And we'll see where that comes in the next two examples. All right, so we're not worried about three-dimensional shapes yet. We will get to that. We're just looking at the front face. The trick here often is just to decide what shapes to subdivide our shape into. And in this case, I think it's most clear if we use a rectangle and a triangle. We could absolutely further divide it into two rectangles and a triangle, but that's unnecessarily complicated because we have formulas for these two pieces. The perimeter, of course, is just walking around the outside of the shape. We can start with either. Let's do the perimeter. To find the perimeter, pick somewhere to start and walk around that shape. So here, if I start in this bottom left-hand corner, we have 9 centimeters, then 4 centimeters up, so 9 plus 4. Ooh, and then we need to know what the diagonal is. We have 2 of those diagonals. This piece over here, which is explicitly labeled, so that's convenient. So this 5 centimeters back here will also apply to here. So I'll add the 5 in, and of course this 4 centimeters. But we do need to know what these two sides are. All right, what's going on here? Let's look at this triangle in a little bit more detail. So we know that the height of the triangle is 3 centimeters. So 3 centimeters, that's the height of our triangle. Do we know the base? Do we know the base? Well, we do know that the entire base of the rectangle is 9 centimeters. We know that the shorter top of it is 5 centimeters, so the base is simply the difference. That'll be 9 centimeters minus 5 centimeters. Gives us 4 centimeters. All right, so that gives us base and height. That's going to be useful for the area, but we don't yet have the two sides. All right, this is where we have to assume symmetry, and we have to assume that it looks like we can cut this triangle in half, and this isn't always going to be true, but for here it works. Cut this triangle in half to create a right angle triangle. So what we now know are these two sides. We know that the height is 3 centimeters. We know that the entire base is 4 centimeters. So that means that half of that triangle base is 2 centimeters. So what we're assuming here is that we have an isosceles triangle. So if you're doing this out in the wild, make sure that you know exactly whether this is okay. It only works for us here that dropping a line down from the point of the triangle down to the base works to subdivide the base by 2 because we have an isosceles triangle. These two sides are exactly the same length, and therefore these two angles are identical as well. All right, what does this let us do? Well, let's just label this side as x, and suddenly, hopefully, we recognize that we can use the Pythagorean theorem here to solve for x. So we know that x squared is equal to 2 squared plus 3 squared, and therefore x is equal to the square root of 2 squared plus 3 squared. Working that through, we find that x is equal to 3.61. Here, because I'm going to give my answer to the nearest whole number, I've decided to add 2 extra decimal places for this intermediate answer. So where were we? We have the perimeter of everything except the 2 slanted sides, and we know that both are 3.61, so I'll just take 3.61 and multiply that by 2. Adding all of that up gives us a perimeter of 29 centimeters. Why centimeters? Because centimeters plus centimeters and so on is still in centimeters. Let's tackle the area. This is where those two shapes are really important. So we'll have the area of the rectangle. Maybe I'll call this area 1. So this will be the total area, or area subscript t. And the triangle, this will be in here. We'll call that area 2. So to find the total, we need area 1 plus area 2, or maybe you're calling them area rectangle and area triangle. What is the area of the triangle? Well, that's going to be length times width. And then the area of the triangle is 1/2 base times height. So the first thing I'm going to do is write out the formula so I know which parts to fill in. It also explains my thinking here. Now I'll replace these with numbers. Length times width, that's going to be 4 times 9. Does not matter to me which one you deem the length and which one the width. Doesn't matter what order we multiply them together, so that's why it's irrelevant. And base of the triangle we said was 4 centimeters and the height 3 centimeters. So this is 4 times 3. Dropping all of that into your calculator will give you 42 centimeters squared. So the total area of the front face, the shaded face of this figure, is 42 cubic centimeters. Let's do one more. We're once again asked for the perimeter and the area of just this front face, the shaded portion. And again, we're to assume symmetry. So to find the perimeter, we will just be walking around the edges of this front gray piece, never crossing through the middle. And to find the area, we're going to have to figure out how to split this compound shape into simpler pieces for which we have a formula. Let's start again with the perimeter. What do we have so far? So for the perimeter, let's start in this bottom left-hand corner. And given 7 centimeters along the bottom. Do we have the height here? Yes, we do. That's 4 centimeters. We don't have the slant, so we'll have to add those two in later. We do have the top piece, so I'll add it in now. That's 5. We have a second slant that will be identical to the one on the right here. So I'm going to label this as S for slant and get to that in a moment. And we have another piece of 4 centimeters. So that's part of the perimeter there. We just need to know what those slants are. This is another situation where assuming symmetry is critical. What that allows us to do is it allows us to see that we have 2 triangles, one on the left, one on the right, that have the same dimensions. That also allows us to figure out for these right angle triangles what the base value is. What is the length of this base? If the entire bottom is 7 centimeters, and we know the top is 5 centimeters, because the difference between 7 and 5 is 2 centimeters, we must have a 1 centimeter base over here and a 1 centimeter base over there. So far, we've got this right angle triangle that has a 1 centimeter base. What's the height of our triangle? Where if the entire height is 8 centimeters, and we know that the triangle starts 4 centimeters up, because the difference between 8 and 4 is 4, this has a height of 4 centimeters. So this allows us to find S, the slant height, using Pythagorean theorem. So we know that S squared is equal to 1 squared plus 4 squared, and therefore S has a value of the square root 1 squared plus 4 squared. Once again, I'll give the answer to the nearest whole number to the nearest 1. So that gives me a hint as to how many decimal places I should have here. I'm going to have 2 additional decimal places in this intermediate step. So I'll record S as 4.12 centimeters. As we had before, we have 2 slants, so I'm just going to multiply that 4.12 by 2. Reaching for my calculator tells me that altogether the perimeter of this object is 28 centimeters. All right, let's try the area. I could leave the divisions as we did for the perimeter. In other words, I could think of this as a rectangle at the bottom, a rectangle at the top, and 2 triangles. But if I don't have to split it up into that many shapes, it might be a little faster. So let's clean this up and see if we can cut it up a little bit differently. What I'm seeing here is a trapezoid sitting on top of a rectangle. So I'll call this area 1 and the trapezoid area 2. So the total area is going to be area 1 plus area 2. Do I have enough information for this? For area 1, just length times width. It's just a rectangle. Right? So it'll be length times width for that portion. And then I'll add in area 2. The area of a trapezoid is 1/2 times the height times base 1 plus base 2. So I just have to identify those pieces. For length and width of the rectangle, I'll use 4 and 7. And length times width is going to be 7 centimeters times 4 centimeters. What about the trapezoid? Well, we already know the height because we had to find the height of our triangle. We said that was 4 centimeters. And what are the bases here? Well, the bases are the bottom that stretches the same length as the rectangle it's sitting on, and this top piece here, which is labeled as 5 centimeters. So we have one base that's 7 centimeters, the other is 5 centimeters. So we have 7 plus 5. Toss that into your calculator. You can do it all in one shot, or you can do it stepwise. We get 52 centimeters squared.